Let's talk about conditional programming and nested loops. So I'm going to go ahead and load in the saved environment file, which gives us a bunch of objects to work with. And we'll start out with conditional 2, some basic if-else statements. So what we want to do is we want to set up a line of code that's going to define a variable, which we'll call y, to be equal to 1 if x is 20 or more, and we want to define y to be equal to 0 otherwise, if x is less than 20. All right, well, how are we going to set this up? Well, all conditional statements look essentially the same. We start out with an if and then a pair of parentheses, a pair of curly brackets, an else, and another pair of curly brackets. And inside the parentheses associated with the if, we're going to put the logical condition that we're going to check. So in this case, we're checking to see if x is 20 or more. And if it's true, the code's going to do one thing. If it's false, the code's going to do something else. So let's go ahead and put in the logical condition. Since we're checking to see if x is 20 or more, we can write that as x greater than or equal to 20. All right, so what goes in the curly brackets? Well, the way the if-else statement works is that when this logical condition evaluates to true, the code inside the first set of curly brackets is going to run. If this instead evaluates to false, it'll skip the code in the first set of curly brackets, it'll hunt for the else, and it will run the code inside the curly brackets right after the else. So we have to ask ourselves, all right, well, what do we want the code to be when this evaluates to true? Well, we want the code to define the variable y to be equal to 1. So we'll put y left arrow 1. When this evaluates to false, what do we want to have happen? Well, when this evaluates to false, we want y to be equal to 0. So we'll go ahead and put y left arrow 0 here. All right, so let's test this out for x equal to 9. We know that when x is equal to 9, this is going to evaluate to false. So the code should skip this set of curly brackets, hunt for the else, and instead run the code inside this other pair of curly brackets. So let's run that and see what's in y. Well, y is equal to 0. So that accomplished it. What about when x is equal to 21? Well, let's go ahead and just borrow that code. Now in this case, x greater than or equal to 20 evaluates to true, so y should become the number 1. And indeed, we find that is indeed the contents of y, so we're good to go. All right, the next question, we want to write an if-else statement that's going to define y to be equal to 1 if x is between 12.2 and 24.7, and 0 otherwise. All right, well, let's go ahead and write the skeleton of the if statement, the if, the parentheses, the curly brackets, the else, and the other pair of curly brackets. All right, so in the parentheses, we're going to put in our logical condition. So we need to figure out how to check whether x is between 12.2 and 12.4, or 24.7. Now, unfortunately, R doesn't have a symbol for between, so we actually need to write this as two logical conditions separated by the and. So to be between 12.2 and 24.7, we need x to be at least 12.2 and ampersand x less than or equal to 24.7. And so this is the way that we write x is between a certain range of numbers. It's greater than or equal to some number and less than or equal to some number as well. All right, so what do we want the code to do when this evaluates to true? And if x is indeed between those two numbers, well, we want a left arrow y to be equal to 1. When it's equal to false, we want a left arrow y to be equal to 0. All right, well, let's try it out. Let's left arrow x to be 9. It's not in this range of values, so this will evaluate to false. And so we should have y being equal to 0 after we run this code. So let's store 9 inside x, run this line, check what's inside y, and indeed, y is equal to 0 here. Well, what if we instead make x equal to 21? Well, we know that this is going to be true because x is inside that range. So if we run our conditional statement and check the constants of y, indeed, it's equal to 1. All right, next one. We want to write a conditional statement that sets the variable y to be equal to 1 if x is even from 2 to 100 and y to be 0 otherwise. All right, so we'll start out with the skeleton. If parentheses, curly brackets, else, curly brackets. What's going to be our logical statement here? What are we checking? Well, we're checking to see if x is an even number between 2 and 100. All right, well, how could I write a vector of just the even numbers in that range? Well, I could write the seek command, and I could say, well, let's create a sequence from 2 to 100 by 2. If I run this little snippet, I see that indeed I have the even numbers between 2 and 100. How can I check to see if x is somewhere inside this vector? Well, that's the job for the %in shortcut. So if x is somewhere inside this vector, the value inside x shows up in this list. What do we want to do? Well, we want to left arrow y to be 1. If it doesn't show up in that list, we want to left arrow y to be 0. So let's check it out. X is odd now, so if I highlight the logical statement, it'll evaluate to false. It's not in this vector here. So if I run this and check to see, well, what's the value of y? Indeed, it's equal to 0. If I borrow this code, put it down here, now have x be equal to 21. Well, it's still odd, so this should be still y equal to 0. And indeed, that's the case. If I said 66, well, now this will evaluate to true. And so the code inside that first set of curly brackets will run. And we find that y will be equal to 1. All right, last one. We want to write a conditional statement that'll set a variable y to be 1 if x is an even number from 2 to 100. Okay, good, we just did that. Or a square number from 1 to 100. And sets y to be equal to 0 otherwise. All right, so how do we do this? Well, even before writing the if skeleton, let's actually work on this logical condition. So we already know how to get the sequence of even numbers between 2 and 100. That's what we can get from our seek command. How can we get the square numbers between 1 and 100? Well, one thing we can do is write the integer sequence 1 to 10 and then just apply the power operator to that. If we do the caret 2, that'll go and one by one square each of the elements of the vector it's squaring. And so we get all the square numbers between 1 and 100. All right, well, we want to check to see, all right, well, is x an even number between 2 and 100, or is it one of these square numbers? So that's two different logical conditions. We can check if one or the other applies by putting the pipe symbol, or the vertical line, in between them. So we want to know, okay, well, is x somewhere inside our sequence of even numbers between 2 and 100, or is x somewhere inside this vector, the square numbers between 1 and 100. All right, let's just try that out because that's a bunch of stuff going on right here. If x is equal to 5, this should evaluate to false because it's not in here and it's not in here. So indeed, that whole thing evaluates to false. Well, what if x is equal to 9? Okay, well, it's not an even number, so this part will evaluate to false. But this part will evaluate to true. So is one or the other the case? Yes. We have one of those conditions being satisfied, and so since they're being separated by the or, if at least one of those conditions is true, then the entirety of the logical condition will return true. All right, what about 36? Well, in this case, both of them are going to be true. We're dealing with an even number, and we're dealing with a square number between 1 and 100. So this or that will, of course, evaluate to true. Okay, well, let's go ahead and write the if statement then. If, parentheses, curly bracket, else, curly bracket. Our logical condition is going to be what we had just written up here. Is x somewhere inside the sequence of even numbers between 2 and 100, or is x a square number between 1 and 100? If so, y is going to become 1. If not, y is going to be becoming 0 here. So let's get rid of that. And let's go ahead and left arrow x to be 9. We know that this is going to evaluate to true because y is a square number, so y should be equal to 1 after we run this. And indeed it is. If instead x is equal to 21, well, it's not an even number between 2 and 100, and it's not a square number. So if we have x being equal to 21 and run this statement, we'll end up in the else part because the logical condition is false, and so we'll see the content of y is 0. All right, let's move on to conditional for, where we're going to write a for loop that utilizes a conditional statement, an if-else statement, to basically recode the elements in a vector to be something else. So what we have is a vector of state names: Tennessee, Kentucky, Oregon, California, etc. And what we'd like to do is we'd like to create a vector called region, where instead of having Tennessee, we have SE, southeast, the region that Tennessee is located in. Kentucky would also be southeast, Oregon would be northwest, and in fact we have a vector, SE, NW, SW, and NE, that tell us basically, all right, the southeast region are these states. The northeast region are these states. So we can visualize what essentially we want to end up with. Region should be the vector SE, SE, northwest, southwest, northeast, northeast, etc. So how do we get there? Well, clearly we're going to need some if-else statements. So how are we going to set this up? All right, so since this is a relatively complicated thing to accomplish, we need to take it slow. We're not going to just dive in, write a for loop that loops through each element of state and does this replacement. We need to make sure that we can get our code working for a specific instance first. So let's go ahead and I'm going to write state test. I'm going to come up with the name of a variable, and let's call this Tennessee. Let's get our conditional statements working for Tennessee at least. All right, so I know I'm going to create a vector called region and be filling in the pieces here. That's what the problem wants me to do. So I'll go ahead and just initialize region to be an empty vector. And I want to write a sequence of if statements to determine, all right, well, what region does Tennessee belong to? All right, well, what I can do is write the skeleton of the if statement. So if parenthesis, curly brackets, else, curly brackets. And now I need to ask myself, okay, well, what am I checking? What's my logical condition? Well, if I think about it, what I want to do is for any particular state code, I want to go through one by one each of these vectors and see which of the vectors that state code exists inside. So does Tn exist somewhere inside the SE vector? Well, in this case, yeah, it does. It's in the southeast. Does it exist in the NW vector? Nope. The SW vector? Nope, etc. So my logical condition is checking to see if my state code here is inside the SE vector or the NW vector, etc. So the way that we can write that is, all right, well, if state.test is inside %in SE, well, then I'll know what I want my code to do. So right now, state test is just Tennessee. SE is defined to be the vector of state names in the southeast. So if I ask, all right, is state.test in the SE vector, that comes out to be true. All right, well, what do I want to do when this evaluates to true? Well, I want to have the region be southeast. Otherwise, well, I want to go and check these other vectors. And in this case, I'm going to omit the else because I'm not going to do the nested if approach. I'm actually going to just write the sequence of if statements just because there's so many different conditions I'm going to be checking. This makes it a little bit more readable. So, all right, if the value of state test is inside the SE vector, region's going to be the word SE. And I kind of see how this is going to end up going. If instead it's in the NW vector, I want to assign region to be northwest. If it's in the southwest vector, SW, I want region to be SW. And finally, if it's in the NE vector, I want the region to be NE for northeast. So what I've done basically is I've gone through methodically each one of these vectors that contain the states from each region and checked to see, okay, is my value of state test inside them somewhere? So right now, state test is Tennessee, so when I run these logical conditions, this first one will be true because it's in the southeast, this next one will be false, this next one will be false, and the last one will be false as well. So if I run the entirety of these four if statements, I'll find that the value inside region is correctly southeast here. All right, well, let's just, let's try this for some other ones. What about Vermont? Well, I know Vermont's in the NE vector here, so let's run through these four if statements. We'll go through that, let's check the value of region, and indeed it comes back as northeast. So this is a nice way of figuring out what region that the state belongs to. I've omitted the else statements because if I did the else statements, I'd end up with a whole bunch of nested if statements. How would that look? Well, let's actually go ahead and write this. So if it wasn't in the SE vector, I'd say, okay, well, else, what's the code that I want to run? And here is where I would check to see, okay, is it in the northwest vector? If so, region's going to be northwest. Otherwise, we see, okay, a lot of curly brackets kind of floating around already. If it's not in the northwest vector, well, we need to go and check the southwest vector, assign region to be southwest. If it's still not in there, well, we've kind of by a process of elimination narrowed it down that region must be northeast in this case. So let's clean this code up actually. Let's put these curly brackets on the lines they're supposed to. Let's highlight this, go to code, and re-indent those lines to look as pretty as we can. So if this was the nested if approach, this is what the code would look like. And this is why I prefer this first approach. It's a little bit neater, it's easier to read, but this works as well. Basically, let's check to see the contents of state test. Is it inside the SE vector? Well, if so, we'll make region SE. If it's not, well, we go and run the code in the curly brackets after the else. And inside that, well, there's a whole bunch of lines of code. What do? Well, we run immediately into another conditional statement, and we check the value of state test. Is that inside the NW vector? Well, if so, we'll assign region to be northwest. If it's not, well, we hunt for the else, and instead run the code inside the curly brackets associated with the else, which is still quite a bit of code here. And the first thing that we do is we run into another conditional statement. We check the contents of state test. Is that inside the SW vector? If so, we're going to assign region to be SW. If it's not, we'll hunt for the else and instead run the code inside that set of curly brackets. So we see that in this case, if we do the nested approach, we only have 3 if-else statements. And that's because if all these 3 evaluate to false, it's not southeast, it's not northwest, it's not southwest. By process of elimination, we know that the region must have been northeast. So if we do the nested if-else approach, we actually only have to write 3 conditional statements. If we do it the sequential approach, which is my personal favorite, we actually have to write in that last conditional statement that checks to see, okay, well, are we in northeast or not? But I feel that this is a lot easier to write and it's a lot more readable as well. But we get to the same place either way. So state test, if it's Vermont, we run these 4 if statements. We see that we have region being northeast. Let's blank that out again so that we can see how the sequential approach or the nested approach works. If we run the nested loops or the nested ifs and check region, we find that it's still northeast as well. It wasn't in SE, it was not in NW, it wasn't in SW. So by process of elimination, region must have been northeast. So it's always going to be up to you how you want to write a whole bunch of if statements. Sometimes you're going to want to write it with the nested approach because that just feels the most appropriate to you. That's fine. Other times you might just want to write a sequence of if statements that covers every single contingency, and that's fine too. So there's always a lot of different ways that we can write our code and get to the same place. Do what feels right to you. You know, whatever is logical, whatever is the most readable to you, whatever makes the most sense, that's fine. So, all right, we got our code working for some specific cases here. So we know how to take, a particular element of our state vector, we call it state.test, and to figure out what the region is. So for any one state, all right, I can figure out the region. I can define region appropriately. But I want to go through and do this for every element of state. So, all right, we're just about ready to write our for loop now. I know I want to loop through the first element, the second element, the third element, etc. So let's go ahead and just get an example working that's going to be able to generalize into that for loop itself. So what I'm going to do is I'm going to define my looping variable to be element. Remember, looping over elements, so that makes sense to me. And I'm going to left arrow that to be 5. Let's make sure we get the code working for the 5th element of state. So if element is 5, Well, why don't I go ahead and say state test is the fifth element of state. But I'm not going to hard code 5. I want to write this so that it's general. I've defined a value called element that equals to 5 right now. And so if I run this, okay, state test comes out to be New Hampshire, indeed the fifth element of state here. So what should my code do? Well, New Hampshire belongs in the Northeast, so region should become the word NE. And what I'm going to do is I'm going to use my favorite approach, do the sequence of 4 if statements, and I'm going to make sure that region comes out to be NE, and it is. Great. All right, so I'm almost there. I'm almost ready to put this inside of a for loop. The only thing is I need to modify exactly what I'm doing with region. So right now we're just defining region to be a single value. I know that as I go through my for loop, I basically want to be putting elements inside the vector region. The first element of region should be the region of the very first state that appears in the state vector. The second element of region should be the second region, or the region associated with the second element of state, etc. So what I need to do, if I'm working with state bracket element, that particular state in that position, I want to be putting the region in that particular position of the region vector. So I want to put some square brackets around region so that this is going to happen as I work my way through the for loop. All right, so elements equal to 5 right now. I know state.test was equal to New Hampshire. So if I run these 4 if statements, check the contents of region, well, here we go. The fifth element of region was defined correctly as NE. I have some NAs here because I haven't defined the second, third, the fourth element. That first element is still NE because when I originally ran this code, I defined region to be NE, and by default, that's going to be that first element there. All right, so we're ready. Let's go ahead and write the skeleton of our for loop here. For parentheses, put it in our in, and then the curly brackets. All right, so we use the looping variable called elements in our example code here. So let's just reuse that definition. We'll call our looping variable element once again. What are we going to be looping over? Well, we're looping through the positions in the state vector. We want to do something for the first element, the second element, the third element, etc. So what we can do is we can create that integer sequence, 1, 2, 3, 4. And I'm kind of lazy. I don't want to count up manually the number of elements in state. So I'm going to say length of state so that it figures that out automatically. In this case, there's 9 elements in this vector, and that saves me from a bit of counting. So I'm going to highlight my looping vector to make sure that it contains all the values that I want to be looping over. Yep, 1 through 9. Great. So element will be equal to 1 first, then 2, then 3, then 4, and run the code inside the curly brackets for each value. And all I need to do is borrow the code that I've already written. This is what I wanted to have happen each time through the loop. I'm going to highlight this, go to code and re-indent. And here we go. So as R runs into the for loop, element will be left arrowed to the very first element of my looping vector, so it'll be equal to 1. I'll define state test to be the first element of state, and then I'll go through my 4 conditional statements. I'll figure out what region that state belongs to, and then I'll left arrow into the first element of region, the right answer here. Then I'll go back, element will be equal to 2. I'll look at the second element of state, left arrow that to state test, figure out what region that belongs to, and left arrow the second element of region accordingly. So I'm almost done. The only thing that I need to do is to make sure right before that for loop I've initialized region to be the blank vector. And that's just because, if I reopen this file at a later time, I haven't done anything to it, I know that I can't put something into a vector until R already knows about it. Now, it already exists in the environment right now, so I'm able to run the for loop without this initialization step. But in general, I'm not allowed to do this. I need to make sure R knows that the vector that I'm going to be putting stuff in is somewhere inside that environment. So we'll have that region left arrow blank vector. We can highlight the entire thing and we can check region. All right, so does this make sense? Southeast, southeast, northwest, southwest, northeast, northeast, southeast, southwest, northwest. Yeah, looks like our job is done. All right, so, well, here's a really big vector. State check contains a whole bunch of state abbreviations. In fact, 50,000 of them. And this is why it's fantastic to have that for loop. Basically, we can say, okay, well, if I want to create a vector called region that has the southeast, northwest, southwest, northeast region labels for each element in state check, well, I can go ahead and do that very easily just by saying, all right, since my code's in terms of the vector state, I'm going to go state left arrow state check and just run my code for every single element in that vector. So now region is 50,000 different elements. I can look at a table of region and I get back what my number of southeast and number of southwests are. All right, so looks like a lot of code for accomplishing this task. And once you get familiar and comfortable with writing these conditional statements and for loops, this will actually go a lot faster. But as you notice, we just took it slow. We got little pieces of the code working one by one. We didn't try to rush and do the whole thing all at once. And when you're learning programming, that's what you really want to do. You want to take it slow, make sure that every single piece of the puzzle is fitting together before you try to write the entirety of what you want your chunk of code to do. So as you're learning programming, you're going to go slow, and that's fine. So kind of going through it methodically, making sure each piece of the puzzle is what you expect is definitely the way to go. All right, let's move on to conditional 5, and that is using if-else. Now, if-else is an amazing shortcut. We don't usually talk about shortcuts in business analytics when we're talking about programming because it's much more important to learn the core concepts of how programming works. But if-else is such a great shortcut that we want to know about it. It basically serves as a shortcut for writing a for loop and a pair of if-else statements here. So what we're going to do is we're going to load up the Reg class library in the Survey 10 data set here. Now in the Survey 10 data set we have a column for the height of the student and a column for the weight of the student as well. And what we want to do is we want to add in a new column called BMI. That is the BMI index of the student there. So let's do Survey 10 $BMI, and let's left arrow that to be the formula that gives the BMI index. Now if I run this right now, I'm going to get an error because it says weight not found. Well, why is that the case? Weight's right here. I can see it. Remember that weight, without anything else, any other modifiers, it's going to try to look for a vector called weight somewhere in the environment. It doesn't see it because it lives inside the Survey 10 dataset. So we're going to borrow that Survey 10 $sign and put that right in front of weight and height. We want to extract out the weight column of Survey 10. We want to extract out the height column of Survey 10 and do the calculation with that. All right, so we've added BMI index. Great. What we want to do is we want to create a new column, another column called overweight, whose entries are going to be a categorical variable with values yes or no, depending on whether or not the BMI index of the individual is 25 or larger. That's the standard threshold set by the health department, and so we want to do this quickly. Now normally this would be a job for a for loop. Basically we want to loop through every single value of BMI. If it is at least 25, we would set the overweight value to be yes. If it's less than 25, we would set it to be no. So if we actually did want to write this as a for loop, well, we could say, something like for I in 1, 2, the length of Survey 10 $BMI. I don't know how many elements this has. I don't want to count that up. So length of this column, basically the length of this vector, tells me how many values there are. What do I want to do? Well, if the value inside of this in the ith position is 25 or larger, then I'd want to create a quantity called overweight, put in the ith position of that to be yes. Otherwise, I want to set this to be equal to no. So this is essentially what I want my code to be doing. I'm going to initialize overweight to be the blank vector here. And I've rushed through that. So I've been writing code for 20 years. This is how I would set up that for loop. It might take you a while to, get your code working for the specific instance and then generalize it so that it goes inside the for loop, etc., etc. But the if-else is going to be a shortcut for exactly what we're trying to do here. So if I run this for loop, make this into a categorical variable by saying let's replace its values by the factor equivalent, I can get a table of all the information I'm seeking. So 200 yeses, 499 nos for the number of overweight people in the survey according to the BMI index. All right, but I don't want to do that here. I want to get practice with the if-else statement. Let's look how much easier it is to do this with an if-else statement. So I'm going to say overweight is if-else, and then a pair of parentheses. So what is the if-else going to do? Well, it's going to automatically go through each element of whatever vector I give it as the first argument. So what am I going to be looking at? Well, I'm going to be looking at the values inside the BMI column of the Survey 10 data set. So for each one of these values in this vector, I'm going to check to see, okay, well, what's my condition? Is it 25 or larger? So I'm going to type in greater than or equal to 25. And in fact, if I just run this logical condition, I get a whole bunch of trues and falses for whether or not that value is at least 25 or not. Now the second argument of if-else is going to be the value that I want when that condition is true. So if the BMI is at least 25, well, I want a yes back. The third argument is going to tell me what I want if that condition is false. So, all right, what's if-else going to do? Well, it's going to go through, and for each element inside this vector here, it's going to check to see if it's at least 25. If it is, it'll return a yes. If it's not, it'll return a no. So I'm automatically creating a vector just like I was doing with this for loop here. So all of this code easily replaced just with the if-else statement. And so I can see that I can run this. I need to create a factor, so I need to left arrow that to be the factor equivalent. But if I run the table, I get the same results back. So this was the for loop approach. This is the if-else approach. Such a useful shortcut, something that we do so often. We change values inside of a vector to be something else. The if-else is basically our shortcut for doing the if-else statement, but inside of a for loop. Do it for each element of a particular vector. All right, so that's conditional 5. The last part is to add that to the Survey 10 data frame. So let's say Survey 10 $overweight. Let's create a new column called overweight, and we'll put the values that we just created into that column. So now we got that column called overweight. It's a categorical variable, yes and no. We're good. All right, let's tackle conditional 7. And what this is going to do is ask us to create 3 vectors, x, y, and z, which are just random numbers from the bell curve here, mean of 0, standard deviation of 1. And part 1 is going to ask us to create a vector called smaller, whose elements contain the smaller of the 2 numbers inside the x and y vectors. So the first element of smaller should be the smaller of the first element of x and the first element of y. The 500th element of smaller should be the smaller of the 500th element of x and the smaller of the 500th element of y. Okay, so how would we go ahead and do this? Well, if you happen to know about the pmin command, that is the pairwise minimum between the vectors x and y, you can actually get everything that we need. So this gives us a nice target for where we're going to end up, but let's figure out how we could do this with an if-else statement. And because we're going to be doing this for each element of a vector, we're going to have to put this inside of a for loop. So let's go ahead, since we know we're going to have to be doing this inside of a for loop, let's go ahead and define index, what we'll eventually have as the name of the looping variable, to be 8. we know we're going to be looping through the first element, the second element, the third element, etc. So index is a perfectly reasonable name for the looping variable. All right, so let's look to see what are we working with. X bracket index right now is minus 0.6. Y bracket index is minus 1.9. So which one is smaller? Well, y is in this case. It's more negative. All right, well, I know I'm going to create a vector called smaller. I'll be putting in the elements of smaller one by one as I loop through the for loop, the smaller of the corresponding element of x and the element of y. So let's get it working for this specific case. Okay, well, my if statement, we're going to have some parentheses, a pair of curly brackets, an else, and some curly brackets again. So I need to ask myself, all right, what am I checking? What's the logical condition that needs to go in here? Well, I'm checking to see, well, which of these two things are smaller. So I could write if x index is smaller than y index, and that's a perfectly reasonable thing to do. If that evaluates to true, I know what the code should do. If that evaluates to false, then I can write what I want the code to do in that case. So let's go ahead, since I'm checking to see which one is bigger than the other, which one is smaller than the other, however way I want to think about it, I can write it this way. So if x bracket index, which right now is minus 0.6, y bracket index minus 1.9, if this evaluates to true, it's not in this case, it's going to run the code inside the first set of curly brackets. If it's false, like what it is here, it'll skip the code inside the first set of curly brackets, hunt for the else, and instead run the code inside the second pair of curly brackets. So, all right, what do I want the code to do? Well, I want to have it put inside the vector smaller in the index position, whatever index happens to be. I'm matching up index with x and y to smaller here. I'm going to put that as the value of the x variable. If x is less than y, we'll put into smaller x, since x is the smaller one. If it's not, well, I'll go ahead and put into smaller in the index position y. Because this evaluates to false, that means y is smaller, so y index is what I want to put in smaller here. All right, so let's make sure R knows about the vector smaller before we actually put an element into it, and let's set the code loose. So I already know that this logical condition is false for this particular instance when index is equal to 8. So if I look to see the contents of smaller, everything's NA because I haven't defined those elements yet. Only the 8th element is defined. I find the value of y because indeed it was the smaller one. All right, that looks pretty good. What about for index of 3? Well, in this case, y is smaller again. This is still going to evaluate to false. So I want to make sure I get an example where that evaluates to true. No, y is still smaller. There we go. Here's one where x is smaller. It's more negative. All right, so if I run the logical condition, I'll find that this evaluates to true. So the code inside that first set of curly brackets will be triggered, and we'll left arrow into smaller the value of x in this case. So if I run this entire line, what I'll find is when I look to see what are the contents of smaller, I see that the 5th element, because index was defined to be 5, is indeed minus 1.74, the value of x in this case. So, all right, I'm actually ready to go ahead and put this inside of a for loop now. I know that my looping variable is called index because I wrote my code in terms of that variable. I might as well reuse it. And my looping vector is going to be the numbers 1, 2, 3, 4, all the way up to 1,000 because the vectors x and y have 1,000 elements, and I want to do something for each one of the elements here. So I'll write the skeleton of my for loop, the for, the parentheses, the in right in the middle, and then the curly brackets. And I'll put some space here. So to the left of the in is the name of my looping variable, which I'm just going to reuse the name index. What are the values that I want index to be? Well, I want to do something for the first element, the second element, etc., 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 all the way out to element 1,000. And instead of actually hard coding 1,000, I'm just going to say length of x. Length of x is 1,000 in this case, but maybe I want to reuse this code, but for vectors x, y, and z that have more elements or fewer elements. Length of x will automatically extract out how many elements are in there. All right, so what do I want to have happen each time through the loop? Well, I want to go and run this conditional statement. If x is smaller than y in that position, well, put in the corresponding position of smaller x. If x is not smaller than y, that means y is the smaller one, we're going to put into smaller the value of y. So I'll make my spacing a little bit prettier, and I'll also make sure that that initialization of smaller happens right before the for loop. If I'm going to put something into the vector smaller, I need to make sure that R knows that smaller exists. So we can set our for loop to work, and we can look to see, well, what's the head of smaller? So here are the first 6 elements of smaller, and head of p min xy should match be the same thing here, and it does. So great, I'm going to put that down here, and we get these two matching up. We're pretty happy. All right, part 2 wants us to do something even fancier. Part 2 is going to define the elements to a vector called smallest, and what we're going to put in smallest is the smallest value between x, y, and z here. So it turns out that this command is going to basically tell us what the answer is going to be. It's the smallest value when we compare x, y, and z together. All right, so let's do something similar. Since we know we're going to have to put our code inside of a for loop and loop through every single index of x, y, and z, let's go ahead and, once again, get our code working for a very particular value of index. We'll have index be the name of the looping variable again. Feel free to choose that. And I'm just going to choose index in this case, have it be equal to 5. So x, y, and z in this case, these 3 values. Which one's the smallest? Well, x in this case. All right, so what do I want to have happen? Well, I'm going to be putting elements into a vector called smallest, so I'll go ahead and make sure that R knows about the presence of this vector. And I need to say, okay, well, how can I write some computer code that'll figure out which is the smallest of these 3 numbers? Well, I'm going to need a conditional statement because I'm going to be checking something. So I'll write the skeleton of this. So how will I know to put inside smallest, say, what's contained in x at that point? Well, x has to be less than y, and x has to be less than z to be the smallest of those 3 elements. So, all right, that suggests that I could put in as my logical condition, if x is smaller than y and x is smaller than z, looking in this particular element of these 3 vectors, well, then I know that I want to put into smallest, in that position, the value x. So if x is less than y and x is less than z, the smallest of those 3 values must be x. Let's go ahead and put that inside smallest. Now, in this case, because I really don't like doing nested if statements, I'm going to just omit the else and instead make sure that I write a sequence of if statements that cover every possible contingency. All right, so this logical condition will be able to determine if x is the smallest. I need to write equivalent logical conditions that determines when y is the smallest. Well, for y to be the smallest, we need to have y be less than x, and we need y to be less than z. All right, if both these conditions are true, if y is less than x and y is less than z, then I know that I want to put inside smallest the value of y in that case. And then finally, the last one for z. If z is smaller than x and z is smaller than y, that means z is the smallest value of those 3, and we'll put in to smallest the value of z in this case. All right, so I have 3 if statements now that cover the entire range of options. So one of these 3 values is going to be the smallest. How can we tell? Well, if x is less than y and x is less than z, well, that means x is the smallest, so we'll put into smallest the value of x. If instead y is less than x and y is less than z, we'll put into smallest the value of y. Or if z was the smallest, well, we'll find that this comes out to be true. Z would be less than x and z would be less than y. So I've covered all 3 cases here. I know that in this case, x is the smallest, so let's see how this plays out. If I run the logical condition, this could come out to be true because x is less than y and x is less than z. So true, we'll put into that position of smallest the value of x. So in this case, we'll see that this evaluates to false because y is not smaller than x and y is not smaller than z. It actually happens to be the biggest one in this case. So the code inside that set of curly brackets doesn't get triggered. So is z less than x? Nope. Is z less than y? Well, it is in this case, but both these have to happen for the logical condition to be true. And so we'll see this evaluates to false. So for every single number inside x, y, and z, exactly one of these three logical conditions is going to be true. And that's why I can avoid the nesting, is that I've covered every single range of options here. So, all right, we got it working for index equal to 5 here. We check to see the contents of smallest. We see, all right, the value of x in this case was stored in there. What about other values? Let's just, make sure our code's working. What about for the very first element? Well, in this case, x is the smallest once again. So, all right, if I run my code, I'm going to find the value of x in that first position. What about index of 2? Well, in this case, z is the smallest. Is my code going to work? Let's see if it puts the value of z in there. It did. What about for the third element? Well, y is the very smallest of the three here. If I run my code, check to see. Yep, the value of y got put in the third element. So I'm pretty much ready to go and write my for loop now. So for parenthesis, put that in right inside, curly brackets, give some space for the curly brackets. What's my name of my looping variable? Well, in this case, I wrote my code in terms of the variable index, so let's reuse that as the name of the looping variable. What values do I want index to take on? Well, I want to do something for the first element, the second element, etc., etc., etc. Every single element of x that exists, I want to do something for it. Let's say for y and z here. So I don't want to count up the number of elements in x. I'll just use length of x to automatically determine that for me. All right, so what do I want to do at each instance? Well, I want to do exactly this code here. I'll check to see is the value of x less than y and less than z. If so, we'll put it into the corresponding element of smallest, the value of x, etc., etc. So we'll highlight this. We'll go and re-indent those lines to make it a little bit prettier. Take out some spaces. And because we're putting something into the vector smallest into a particular position, I'm going to actually go ahead and initialize it right before that for loop. And let's go. So we've gone through, and in a flash, loop through all 1,000 elements of x, y, and z. We can go and check our work. Move this down here at the bottom. Let's look at the first few elements of smallest. This command's supposed to do the same thing, and great, I'm getting that to match up. So once again, I just took it slow. When you're learning how to program, do conditional statements, for loops, it's best to very slowly work your way up to what the final bit of code is going to look like. So here we just slowly wrote those conditional statements. We did a lot of example checking to make sure the code was doing what we wanted it to. And we were able to build ourselves up to getting the code working inside of the for loop. All right, let's move on to NestedFor 18. And this is a pretty interesting question. So in this case, we're going to make a plot, and we'll talk about what's going on here. So essentially what's going to happen is that a new branch of a chain store is going to be put somewhere on one of these black dots here. We basically have 100 different choices for where to put the new store. And depending on where the store is put, well, the revenue is going to be a little bit different. These red dots represent population centers, and we'd like to place the new store so that, we're the closest to all three population centers, but the bigger red dot gets a little bit of priority. There's more population there. So the question becomes, all right, where do we put this store so that the revenue is going to be the largest? And in this case, the analytics team has actually gone through and developed an equation that tells us that depending on the x-coordinate and y-coordinate where we put the store, the revenue is expected to be given to us by this equation. So for example, if I said, well, let's go ahead and put it at x is equal to 6 and y is equal to 5, this guy right here, x left arrow 6, y left arrow 5. In this case, the revenue is going to be 6.46. Now, there's a little bit more to the puzzle though, because while the revenue of the store at this location might be this quantity, it costs some amount of money to build the store at this location. The cost to build at each one of these coordinates is slightly different. And in fact, we have that information in the matrix cost. This tells us, all right, if I want to build that store at a value of x of 6 and a value of y of 5, well, that's going to cost me 0.4. If I want to build it at x of 6 and a y of 4 here, that's going to cost a lot here. So not every location is created equal. Some cost a lot more than others. So the question becomes, all right, where do I want to put this store to balance the cost and the revenue that will result? So I essentially want to loop through all 100 of these positions, but this is going to require me to essentially do a nested for loop because there's two things I'm looping over. I'm looping through possible values of x, and I'm looping through possible values of y. For each value of x, like x is equal to 4, I want to methodically go through each value of y, and I want to do this for each one of those values of x here. All right, so big question, and a lot of code that's going to go on here. We want to take it slow. And so we're going to build this up in steps. So the question says, all right, let's imagine that management has decided that this store will be built with y equal to 6. So I'm going to left arrow y to be equal to 6. So it's going to be built somewhere on this line. If y is equal to 6, well, which of these 10 choices of x is going to be the best choice? That's what we're going to develop first. All right, so our goal is to write a for loop that calculates the net revenue, the revenue minus cost, for each of those 10 possible values of x. All right, well, we don't want to just dive in and write that whole for loop. We want to do this slowly. Let's just get the code working for a very particular value of x. Let's try x equal to 4 just for illustration. All right, so when y is equal to 6 and x is equal to 4, our revenue in this case is given to us in terms of this equation. I'm going to use the left arrow sign instead of the equal sign here. What's the revenue? All right, let's check that out. If we place the store at y of 6, x equal to 4, our revenue is 6.1. However, that incurs a cost. If I look at the cost matrix, well, I can look at a particular element of the matrix by turning on the square brackets, but since cost has rows and columns, just like a data frame, I need to have a comma right in the middle. Which row do I want? Well, I want the row 4, but 4 is just x in this case, so I'll put x to the left of the comma. What column do I want? Well, y. I want the sixth column here. So the cost associated with building the store at a position x of 4 and y of 6 turned out to be 0.1. So the net revenue here, the revenue minus cost, works out to be just a little bit above 6. All right, well, that's my answer for when y is 6 and x equal to 4. What about when x is equal to 1? Well, let's change that up. Let's calculate the revenue at that location. Ooh, not very good. The cost of that is actually pretty big. The net revenue turned out to be negative here. So for y equal to 6, there's some optimal choice of x, and let's go ahead and figure that out. So what we're going to do is we're going to create the elements of the vector net revenue y6 to initially be blank, and we'll use that for loop to loop over the possible values of x and calculate that net revenue for each possible value of x. All right, well, let's go ahead and write the skeleton of that for loop. We'll put the in inside the parentheses, and we'll have to ask ourselves, okay, well, what do we want the name of the looping variable to be? Well, I just wrote this code by left arrowing into the x coordinate the value x here. So let's just reuse that name. So let's have x be equal to 1, then x be equal to 2, then 3, then 4, etc. So my looping vector is going to be just the integer sequence 1 through 10. I want x to be equal to 1, and I want x to be equal to 2, 3, 4. I'm going to try all possible values of x. All right, now what do I want to do for each one of those values of x? Well, I want to store into the net revenue y6 vector. So I'll turn on some square brackets, and the first time through the loop, x will be 1. I want to put into the first position of this vector some number. So we can bracket x that because x is going to be equal to 1, then 2, then 3. So we'll be putting into the first, the second, the third element. So it works out nicely. What do I want to put in? Well, I want to put in the revenue minus cost. So let's go ahead and just borrow that equation for revenue. And I know that I'm going to take the revenue from that location and subtract off the cost at that location. So I can just copy and paste this. Great. All right, so when R runs the for loop, x will be left arrowed to 1. We see we calculate that revenue for x equal to 1, and y has been left arrowed to 6, way, way, way back up there. It'll get the revenue and then extract out the cost associated with that location, subtract the 2, and store into net revenue y6 in the corresponding position, depending on what x is, the net revenue here. So let's run it and let's check to see, all right, what are the contents here? We have a sanity check where the first few elements should be these numbers, and it looks like we're working out pretty good. All right, so we can just scan through here and we say, okay, well, where's the biggest value? Well, in this case, it looks like x equals to 3 would be the best choice. So I could say, all right, well, where's the max net revenue? That's this value. And I'd like to know, okay, well, which position was that located in? I can use that which command, net revenue, and then in square brackets, which net revenue is equal to this max value. So which net revenue y6 was equal to the max? Well, that's position 3. What's the value in position 3? There we go. So this which statement right here lets me know where the optimal location of x was, and it looks like I've got my code working for y equal to 6. But now what I want to do is I want to do the same thing for y equal to 1, y equal to 2, y equal to 3, etc., etc. So I need another for loop, a for loop that now loops over the possible values of y. So what we're going to do in this case now is instead of just creating a vector that stores the revenues for different values of x, I really want to be doing this with a matrix because I want to be doing this for all possible combinations of x and y, basically a two-dimensional object in this case. We're going to go ahead and create the matrix called net revenue. Trying to see if I have that definition up here. So let's go ahead and create this then. So what we're going to do is we're going to create the matrix net revenue to initially be all zeros. We want 10 rows and we want 10 columns. All right, so initially we start out with all zeros. And what we want to do is put in, all right, well, what's going to be the net revenue for each combination of x and y. So x will label our rows, y will label our columns. And that's consistent with the notation that we've done so far here. All right, so how do we go and do this? Well, we've actually gone and done almost all of the heavy lifting already. We have our code working for a particular element of y, so now we just need to make sure that the code we've written will work inside of a for loop that goes through each possible value of y. So what I'm going to do is actually just start out by typing what I want my for loop to look like. Since my code was written in terms of the variable just called y, I'll just reuse that as my looping variable. What values do I want y to be? Well, I want to go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do I want to do for each one of those values? Well, I want to store the net revenues for all possible choices of x, and then put that in my net revenue matrix. So what I'm going to do is actually just go ahead and borrow the code that I wrote for when y was equal to 6. So what I'm going to do is, instead of actually storing it into a vector, well, I'm going to store it into the relevant location inside the net revenue matrix directly. I've already initialized it. It contains 0. So I'm going to get rid of that vector name and just modify the code accordingly. I'll highlight this, go to re-indent lines. So for a particular choice of y, like the first time through the loop, y is going to be equal to 1. what we are going to do is we're going to loop through each possible value of x from 1 to 10, calculate the revenue for that choice of x and y. The first time through the loop, y is going to be equal to 1, x will be equal to 1, then 2, then 3, then 4. We get that revenue, subtract off the cost, and, well, we can go ahead and store into the relevant position of the net revenue matrix that net revenue. So the first time through the loop, y is equal to 1. X is going to be 1, 2, 3, 4, all the way up to 10 here. So we'll go through and essentially populate that first row of the net revenue matrix. Here is x is equal to, or the first column of that net revenue matrix, sorry. So because y is labeling the columns, it's going after the comma here, we go through and define the x equal to 1, the first row, x equal to 2, the second row, x equal to 3, the third row. So the first time through the loop, when y is equal to 1, we'll go and define every single one of the values in that first column. So let's just confirm that that's what's working, or that's working here. Let's go ahead and manually left arrow y to be equal to 1 and run this small part of the loop. Let's check to see, well, what is net revenue equal to? Yeah, I populated that whole first column here. When y is equal to 2, kind of manually advancing the for loop, just pretending like I'm R. Second time through the loop, y is going to be equal to the second element of the integer sequence 1 through 10. And now I've populated the second column. So I'm pretty much good to go. So here I was left arrowing y to be 1, I left arrowed y to be 2. This for loop is going to automatically do that left arrowing for me. That first time through the loop, y will be the number 1. Then it'll be 2, then it'll be 3, etc. So let's go ahead and run the entirety of this thing. We can actually look to see if it did its job. Yeah, we've gone through, and for y equal to 1, we loop through all the possible values of x. For y equal to 2, we loop through all the possible values of x, and we're storing the revenues associated with each of the possible combinations. So great. All right, well, we're given some sanity checks. What's the mean of net revenue? 3.16 right up here. So we can also check to see, all right, what happens to be the values inside here, and what's the median in one of these things you were entering up onto Canvas. All right, so we have all these values. Where's the best choice? Where's the biggest number? Well, my eye is immediately drawn to this, but it's really easy to, overlook something here. Is this the optimal location? Well, we need to figure that out. All right, so we want to report the optimal XY location to build the store. So we want to know where inside this matrix do we find the biggest value. Well, what is the biggest value? The biggest value of net revenue is indeed that 92.4. Now I can see that right here. I see that corresponds to x of 4, the row position, and a y of 8, the column here. But I need to get the code to automatically tell me that. Well, I know the which command tells me where inside of a vector it finds elements that meet a certain condition. And I just need to modify that a little bit when I'm dealing with a matrix. So if I were to say, well, which element of net revenue is equal to the maximum value, if I were to run that, well, I get back kind of a weird result, element number 74. So this works when the object that we're referencing is a vector, and it would tell us, hey, the 74th element of that vector is where we find the biggest value. But in this case, we have a matrix. We actually have two numbers here. We want the row, we want the column. So how do we get that out? We add in the additional argument array index equals to true. And so it says, row 4, column 8. Indeed, row 4, column 8, 92.406. So x of 4 and y of 8 is the optimal location. So where is that? Well, here's x of 4, here's y of 8. It turns out, actually, that we want to put our store right here, very close to this population center. Even though this one has more people and we actually have a higher net revenue, the cost is so much higher associated with this. If you really dive into the details, it's actually the most advantageous to build it right here. All right, last question, NestedFor 20 here, deals with inventory control, a big problem in supply chain analytics. So when your product's getting low in stock, you want to reorder more so that you don't have a stock out and miss potential sales here. So we have two choices, basically how much are we going to reorder, which we're going to call the quantity, and at what point do we want to place that reorder here. So how low does the stock need to go before we place this reorder here? So let's imagine that the analytics team has developed a formula that tells us what the cost is for a particular inventory control policy. Based on the reorder point and the reorder quantity, this is the cost associated with that policy. So if you have too much in inventory, where you're wasting money, in storage. If you don't have enough inventory, you're losing money because you're missing demand. So let's imagine this equation here captures the trade-off between those two. So if point was equal to 7 and quantity was equal to, say, 20, what would be the cost associated with that policy? Well, it turns out to be 9,132. All right, so if we do point is equal to 30, let's just confirm this equation is working, and quantity is equal to 50 here. It says that we should get a cost of 38.97795. Nope, so we need to change that number. Thought I had updated that, but I had not. All right, so what we want to do is we want to design a nested for loop that considers all integer values of point from 1 to 200 and all integer values of quantity from 1 to 200 as well. So there's a lot of choices going on. All right, what's going to be our reorder point? Anywhere from 1 item left in stock to 200 items left in stock. How much are we going to order? Well, anywhere from 1 to 200 items. We want to look at all possible combinations of these two quantities. And that's a lot. So for each choice of point, we have 200 choices of quantity. We have a total of 40,000 different policies to consider. We want to find the best one. Okay, so how do we go about doing this? Well, what we're going to do is we're going to create a matrix called policy cost, 200 rows, 200 columns. The entries of policy cost are going to be the costs associated with a particular policy. So the way that this is going to work is, for instance, if quantity is 30 and point is 20, we're going to put into row 20 and column 30. So the rows are going to correspond to the reorder points. The columns are going to correspond to reorder quantities, the cost associated with this policy. So if I run this code here, I find that the cost of the policy where I reorder stuff when I reach 20 in stock and I reorder 30, that's a cost of 6468.8. So this matrix is so big, I actually can't even print everything out to the screen. There's so many elements here. So I'm going to need to write a program to loop through every possible control policy and figure out, well, which one is the best. All right, so how are we going to do this? Well, we're going to slowly work our way up to this nested for loop. So we're going to start out just by saying, okay, quantity is equal to 30. And we're going to figure out how we can write our code to go through every possible value of point and store those costs inside our policy cost matrix. All right, let's get our code working. For a very particular case, we've already looked at quantity of 30, point of 20, kind of know what to anticipate here, so let's do this. So what we want to do is we want to store inside policy costs the cost associated with this policy. Well, I have an equation for this that I'm going to copy over to here. I just need to figure out what do I want to put to the left, what I want to put to the right of my comma here. Well, I want to make sure that the rows are corresponding to the point and quantity are corresponding to the columns, consistent with what I have up here. So instead of hard coding 20 and 30, like what I had for this first example, since point is defined to be 20 and quantity is defined to be 30, I'll use those variable names instead. So point is 20, quantity is 30. We're storing into that relevant position inside policy cost, the cost of that policy. So, all right, let's go ahead and loop through all possible values of point. So how can we do this? Well, we can write the skeleton of our for loop. For and in inside the parentheses and some curly brackets. What do I want the name of my looping variable to be? Well, I just wrote this code that used the word point. So if we're going to loop over all values of points, and I've left arrowed point to be 20 for my specific example, it makes sense to just reuse that name. What's going to be my looping variable? What values do I want point to equal to? Well, I want it to go through point of 1, 2, 3, all the way up to 200. And what do I want to do for each of those values of point? Well, I want to calculate the cost associated with using that point, conveniently stored in the variable point, for my value of quantity, which I'd left arrow to 30 up here. So how will this for loop work? Well, point will be left arrowed to 1, the first element, and we'll put into the first row, 30th column, quantity is 30, the cost of that policy. Then point will be left arrowed to 2, and I'll put in the second row, 30th column, the cost of that policy, etc., etc. So we run that, and we have a quick sanity check. It matches up. And so what we've done is we've gone through and basically defined every element in the 30th column, so when quantity is equal to 30, what the costs are associated with those policies. And we see a pretty big, diverse array. Some cost a lot, some don't cost all that much. Now what I want to do is to basically go through every possible value of quantity now, and for each one of those values, do this loop. I want to loop through all possible values of point and store into my matrix what the costs are of those policies. So, all right, we have our code working for a particular value of quantity. Now we want to loop through every value of quantity. So let's go ahead and write the skeleton of our for loop. Because we got our code working in terms of a variable called quantity, we left arrowed it to a very particular value. Let's go ahead and just reuse that as the name of our looping variable. So what values do we want quantity to be? Well, we want it to be 1, 2, 3, all the way up to 200 here. And what do we want to do for each one of those values of quantity? Well, we want to loop through every possible value of policy, calculate the cost, and store it into our policy cost matrix. But we already just wrote that code. We just wrote that right here. This loops through all values of point and puts into that policy cost matrix the cost associated for that policy. So inside the curly brackets associated with our for loop over quantity, we can just reuse that code. We already have our code working that loops through the values of point from 1 and 200 and puts into the relevant position of policy costs, those costs right there. So that's great. And in fact, because we were smart about this and we never hard-coded any particular numbers in here, we just represented what the reorder points were by the variable point and the reorder quantities just by the variable quantity. We don't even have to modify anything whatsoever. So how is this going to work? Well, we start out by left arrowing quantity to 1, and we run what's inside the curly brackets. And it just so happens that there's a for loop inside the curly brackets. So point will be equal to 1. We define the first row, first column of policy cost to be the cost of that policy. Then we loop to point equal to 2, get the policy cost. Point equal to 3, policy cost. Quantity is still 1 here. We're looping through every single value of point first. We complete this for loop until we run out of code with the for loop associated with the loop over quantity here. Then finally, quantity is equal to 2. We loop through all possible values of point. Quantity is 3. Loop through all possible values of point. And so we see that we're slowly but surely populating every single element of policy cost. Here's our sanity check. We get that working out. That's good. So we're pretty much ready to go. Where is the minimum policy cost? All right, well, I know what the smallest policy cost is. That's 831.8. But where is that in this matrix? It's a huge matrix, 40,000 elements, so I can't just look at it and be like, ah, I see it. So what I need to use is that which command again. So if I had a vector, I could just say, well, which element of policy cost is equal to the smallest policy cost? But policy cost is a matrix. It's not a vector. So if I run this, I get the rather cryptic result that 15,481. Where does that correspond to inside of a matrix? I have no idea. I really want the row and the column numbers instead. So because it's a matrix, I'm going to add in one additional argument, arr.ind equals to true, short for array index, and this will actually print out the, arr, the row and the column number associated with that. So is that right? 81st row, 78th column. Yeah. All right, so we've gone through 40,000 different inventory control policies. We've auditioned 200 values of point, 200 values of quantity, considered every single combination of those two, and we've determined that, all right, there is an optimal choice here. It looks like we want the value of the reorder point to be 81. So every time the amount in stock dips down to 81, we want to place an order for 78 additional items.